Okay. So yeah, let's get started. What is artificial intelligence? Artificial intelligence is an extremely broad branch of computer science. It's a vast collection of tools used to solve many challenging problems in computer science, such as natural language processing, or NLP, perception, like computer vision, image recognition, etc. AI is closely related with data science. It's an emerging field. You probably heard all about it. There's like a ton of hype around it, concerned with extracting useful information out of raw data. Machine learning, ML, is a subfield of AI in which trainable algorithms are used to solve traditionally hard problems, like NLP, computer vision, etc. There are different ML algorithms used today. In this specific presentation, we'll just introduce neural networks and perceptrons, though in like 2 lessons from now, we'll look into some of the more interesting and robust models, such as convolutional neural networks and recurrent neural networks. So now I'll pass it off to Mr. Du.
All right. I guess I'll switch to be the screen sharer. All right. So before we talk about neural networks and stuff, we're first going to talk a bit about data, because machine learning really is just data science, or an application of data science. So let's talk about data. So as you guys probably all know, as advanced room CS Club members, computers store data as numbers, right? As strings of bits. And what's pretty interesting, I guess, or what's relevant to this lesson is that all information can be represented as a number. And while that might sound weird, because like, how do we represent like the color blue as a number, right? Well, the color blue is qualitative data, right? Like if you've taken science class, we know that color, or maybe like something that you feel from sense, would be qualitative. So you describe it with words. Well, in data, well, I guess in data science, there are 2 types of data called numerical and categorical data. Numerical data is quantitative data, which is, well, obviously, since it's numerical, it can be stored as a number. And some examples are age, RGB value, audio pitch, and price. And categorical data is just qualitative data. And what categorical data means is that it's just categories that can take on numerical values. So, for example, if you're storing data about people, then a person's gender can be represented as 0 for male, 1 for female, or 2 for other. So some examples can be like male/female gender. It can be nationality. It can be vehicle manufacturer. And obviously, like the way you represent categories as data kind of matters, because if you try to store, if you try to say like, if you try to store every single person and you make like their name, you make their name a category. So you have Trevor Du as 0, Cristian Bicheru as 1, and then so on for every single person. Then you need a really, 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 really big number to, or a lot of space to be able to store like every single person, I guess. But yeah, it's possible to store all types of information as a number, and that's relevant for today. So in machine learning, data is stored as vectors, which is a sequence of numbers, just like C++ vectors, I guess vectors of int, or vectors of floats, in the form of data points. So you guys have already 100% worked with vectorized data if you've ever seen this thing, which is the Cartesian coordinate system. Because points on the Cartesian plane are just data points that store an x and a y value. And ordered pairs, so like the 0, 0, or the 5, 2, or the 1.5, and -3, they're actually just 2D vectors, right? They're vectors of length 2. And the length of a vector is its dimensionality. So a 2D vector is plotted on a 2D plane, like the 0, 0 2D vector is plotted on a 2D Cartesian coordinate system. 3D vectors are plotted in a 3D space, and 256D vectors are plotted in a 256D space. So what I mean by 256D space is, like, imagine a coordinate system with 256 axes. And since we're 3D people, that's kind of hard to imagine. But if you kind of like think of them as, I guess, Cartesian coordinate systems, so like x and y planes, except with more axes, then that's like how they work. So each axis or each number in a vector is one attribute of the data. So imagine, like, for example, in a distance time graph, then one axis of the distance time graph would represent time, while the other axis would represent distance. When you have something like a 256D vector or a 256D space, you could have one axis represents age, another axis represents uh, gender, another axis represents nationality, another axis represents height, another axis represents shoe size, and so on. So that's how we store data as vectors. And then you can plot points in these space. You can plot these vectors in that space. So what we're concerned with for today, I guess, uh, one of the many tasks that machine learning can do is statistical classification. And what classification is the process of separating a group of data points into classes. So for example, if you had a bunch of cats and a bunch of dog data points, you would have Mr. Computer here split them into cats and dog groups. And obviously, machine learning, there's always some error. So you might accidentally put a cat in the dog group, or you might put a dog in the cat group. But the goal of machine learning is to have the most accuracy possible. I guess not for it to be accurate 100% of the time. So here's an example. I found a random graph online with a bunch of blue and orange points, and we're going to pretend that this is a graph of, well, each data we're going to pretend that each data point is a student, and the x-axis is the number of hours slept the night before the exam. And don't ask why you can sleep for a -4 hours, because I just chose a random graph. And the y-axis is the amount of time that the student has studied leading up to the exam. So orange points are students that have passed, and blue points are students that have failed. And pretty much our job as data scientists is to find this green line that separates the blue and the orange dots, so the passing and the failing students, is, well, as accurately as possible. So as you can see with data like this, there are a lot of factors to take into consideration. You might have, for example, like these guys who are below the line, but they still passed. So our model isn't 100% accurate, but it's a pretty estimation based on sleep time study time of whether a person would pass or fail the exam. So if the point is below the line, you fail the exam, well, or the model predicts that you failed the exam. And if you're above the line, then the model predicts that you passed the exam. So let's talk about perceptrons. And this is a type of neural network. And it'll be the first type, or the introductory type, that we'll be talking about today. So what are perceptrons? They're a basic unit in a dense neural network. And a dense neural network is just the type of neural network that we'll be talking about. And it's the type that you usually see, like where we have all of these circles and lines connecting them. So the circles are called neurons, and the lines are called synapses, or weights. And neurons and weights are really just numbers, but since a lot of machine learning and neural networks are based off of actual biology, they like to name them like neurons and synapses. So there's usually also an extra input neuron called the bias, and the bias is always set to 1, and the weight of the bias is called B. And to compute the output neuron value, so the Y value right here, you would perform this operation, which is you would take each input neuron, multiply it by its weight, and then you would add them together. So x1 multiplied by weight 1 plus input 2 multiplied by weight 2 plus all the way to input m multiplied by weight m. And then you add the bias. So note that the input neurons and the weights can be represented as vectors, right? If you have a vector capital X is equal to x1, x2, all the way to xm. You have a vector capital W is equal to w1, w2, all the way to wm. Then y can be computed by taking the dot product of W and X, right? Because the dot product, you're just multiplying each corresponding value and then you just add them together. So then our formula for calculating the output neuron, or Y, is Y equals WX plus B, which might look pretty familiar if we've all taken grade 9 math, because this is just a linear function, right? So perceptrons represent linear functions. They represent lines, planes, or higher dimensional blights. And to train a perceptron, what you would do is you would adjust the values of each weight and the bias until from an input, so like from an X vector, it can learn to separate data points into categories. So let's take a look at an example. An algorithm gradually updates the weights of a perceptron. So these values, W1, W2, W3, the synapses, it updates the weights of the perceptron to train it to classify flowers, this one. The line is a linear function, so this line, the thing that's like kind of turning and separating the red and blue regions, is the linear function that is represented by the perceptron. When the perceptron output is positive, the point is a blue X. And when it's negative, then the flower is a red square. And let's see. And each data point is just two values, a 2D vector of sepal length and petal length. Then we use that to try to train something to separate these two groupings of points. But so far, what we've been talking about are binary classification tasks, meaning that they classify data points into only two classes. For example, you've got the blue flowers and the red guys. But what about multi-class classification tasks? Like if you want to classify an image into, let's say, a cat, a dog, an airplane, and a person, into those classifications. Well, a single output neuron won't do, right? Because even in this one, we're only looking at whether the output's positive or negative. So usually for classification tasks or multi-class classification tasks, data vectors are one-hot encoded. And imagine like I'm doing air quotes here. So a one-hot vector is a way to represent categories pretty much with vectors. And in a one-hot vector, each number in the vector ranges from 0 to 1. And only one number is set to 1 while all other numbers are set to 0. So for example, if you had three classes, dog equals 0, cat is 1, and plane is 2, then a vector that represents the dog class would be 1, 0, 0. A vector that represents the cat class would be 0, 1, 0. And a vector that represents a plane would be 0, 0, 1. So neural nets usually don't output a y value like in the previous examples. They output confidence values for each number in a one-hot vector, so for each class. And from the previous example, so this example with the dogs, cats, and planes, a neural net, let's call it NN, which takes an input vector of x, might output an output vector 0.2, 0.75, 0.05. And what this pretty much is saying is that, well, it's slightly confident that the input vector x is a dog because, well, 0.2 is, well, not exactly 0, but it's pretty far away from being 1. And the middle number, so the cat number, is 0.75, so the network's pretty confident that x is actually a cat. And in the third number, so the plane number, uh, this one, 0.05, the neural network thinks that it's pretty much there's no way that this can be an aeroplane. So that's pretty much how neural nets work with vectors and data. So let's oh wait, there's one more slide. My bad. So this is a neural net that outputs one-hot vectors. So it looks a lot like the basic perceptron. So like this, except it is 3 output neurons. And notice that this is actually just 3 perceptrons, right? Like you have the inputs here all leading into this top output neuron. Then you have all these inputs feeding into this middle neuron, and then you have all the inputs feeding into this bottom neuron. So this neural network is actually just 3 perceptrons. And the perceptrons take the same input, and each perceptron outputs to one category of the one-hot vectorized output. So this is basically what our networks look like for now. I think I'll pass on to Cristian now, who will talk about how we'll actually train perceptrons.
Yep. Thanks, Trevor. Let me just share my screen. There we go. That should be good. Okay. So yeah, now we'll talk about how we actually train perceptrons. So we now know perceptrons can be used to classify linearly separable data, but perceptrons aren't like created knowing how to perform this task. If you just randomly select the weights and the biases, it won't make any like decent predictions. Perceptrons must actually be trained on or fitted to a training dataset before they can make any reasonable predictions. The trained perceptron can then be evaluated on a separate validation dataset to gauge its performance. And then, yeah, a quick note is it doesn't make sense to evaluate a perceptron on like the same dataset it's trained on, since it doesn't tell you anything about the quality of the predictions, just how well it memorized the training set. We have an example later on where we do evaluate it on the training data set, but that's just to prove that the algorithm is actually like learning something. In like if you were to train like a real model on like a classification task, you definitely don't want to train it on the same data set. What you usually want to do is split the data set, like your raw data set, into like 80% of the values can go into a training one where your model can train on those values, and then 20% go into a separate data set solely for evaluation that your model never trains on, so that it's like fresh data and it's like a fair validation for your model. And then, yeah, so perceptrons are trained by running them over input data and comparing the outputs with the actual values from the dataset, and then adjusting the parameters accordingly. So in order to quantify the error between the predicted output and the true output, a loss function is used. And we'll talk more about that in the next slide. The stochastic gradient descent, or SGD, algorithm is used to train perceptrons based on the output of a chosen loss function. So now let's take a look at loss functions. So a loss function, evaluated on the output of a neural network and the true output from the data set, outputs a real number representing the error or cost between the two vectors. So one common loss function, and the one we'll be talking about in this presentation, is the mean squared error, aka the MSE loss. So MSE is a pretty common loss function, and it usually works pretty well, especially for regression tasks. The formula for the MSE is this here. So basically what it says is you take the difference between like your predicted value and what the value is supposed to be, you square it, and then you take the average over all of the outputs of your perceptron. And then this is more commonly just written like this, where y hat is like y predicted, and then y with nothing on it is just like the true value. And so let's just see a quick example. So if the y predicted of a neural network is this vector here, just some sample numbers, and the truth is this vector here, what is the MSE loss between the two vectors? So we just plug and chug into our formula, and we get, take the difference square, blah, blah, we get 27.75. Let me just see, I got it. Okay. So yeah, that should kind of explain how loss functions work. You just input your neural network's output predictions and the true value from the data set, and then it spits out some number basically telling you what the error is between these two vectors. So yeah, now that we know how to compute the loss or cost of our perceptron predictions, we need to figure out a way to update the weights and bias values to better fit the dataset. And this is done through stochastic gradient descent, or some variation of it, but for now we'll just look at SGD. I see a question from Ridwan. Can the second set have to be the same as the first set? What do you mean by that? Like the same length? Yeah, so it has to have the same dimensions for MSE. It's different for like there's So in classification tasks with like neural networks, there's stuff like it's called sparse categorical cross entropy loss, where the output where your output from your network is a one hot, but your data set is a class number. So then it's like technically not the same size, but really it just converts the class number to a one hot and then compares it element wise. So it basically is. But yeah, that's like, yeah, we'll talk more about that 2 lessons from now. So don't really worry about it. But generally, yeah, it has to be the same dimensions, especially for MSE. One hot, Trevor talked about it earlier, but a one hot vector it's basically like an array of numbers where only one number is set to 1 and all the other ones are 0. So for example, I'll just type it in chat, like something like this would be a one hot vector. And basically this represents like the value 2, I guess, in a neural network. Yeah, when it's Eric brings a good point. Yeah, when it's the output of a neural network, it's the sum of the numbers have to be 1 because it represents probabilities. Yeah. But yeah, it can also be the input, and then in which case, yeah. But we'll definitely see a lot more of this when we start talking about CNNs and RNNs and whatnot. So anyway, now that we know how to compute the loss of our perceptron predictions, we need to figure out a way to update the weight and bias values to better fit the data set. And this is done through an algorithm like stochastic gradient descent. There are some variations, but we won't look at them for now. We'll just look at SJAM. And so we can kind of see how that works here. You basically have some initial weight, and this is like your loss function, and this is like your weight. So like different values of the weight correspond with different losses. And we basically just want to follow that towards a minimum. And so I'll kind of show you the formulas for that here. So for a simple perceptron, the formula for updating the weights using SGD is the new weight is the previous weight minus this constant eta times the rate of change of the loss function with respect to the weight. So yeah, you know how like a simple perceptron has just a weight and a bias, right? One input, one output. You update the weights each epoch based on this formula here. And eta is the learning rate of your model. So it's just a hyperparameter that you choose. Generally, I guess I'll talk more about it later when we get into overfitting and underfitting, but it's like a bit of an art picking it. There's not like a good like bulletproof way to pick this number. You kind of just have to like play around a bit, get it, but you can kind of get a good sense of what a good learning rate is. And then this part here is just the derivative with respect to the cost function or the loss function. And I'll show you that in the next slide. So we said we would use the MSE as our loss function. So if you plug that in and compute the derivative, you get this formula here. So you can see that for the weights, it's just every single epoch or like every single time you run through the data set and train, you update the weights based on this formula here. So it's just basically the average of this here. It's 2 times the difference in your predicted value and your true value. So yeah, for those of you who are taking calculus, you'll know that's just like really simple, the derivative of a power, right? And then here, it's the same thing. It's just like calculus. I know a lot of you haven't done calculus yet, so I won't spend too much time on that. But yeah, that's if you are really keen about it, you can try and driving these formulas yourself based on this here. But yeah. So tying it all together. Now that we've covered the necessary math to train a perceptron, you can train on any data set now. And you can see an implementation of this MSE loss here in Python at this link here. I'll link the presentation after so you guys can click on it. But if you run it, you'll get an output like this. So I just like made like some random values for like a data set. These don't really have any meaning. And then here's the model at the start. So it just has random weights and bias. So it's just like some random line through space. You can see it has no correlation. And then we run the model for like a bunch of epochs. And then afterwards we replot it, and you can see it's like a perfect fit to the data set. Well, there's some variance, but you can see that it is training that the code is working, because it does go through the middle of all the points. And oh yeah, so here's that picture I was going to talk about. So basically with this code, like you'll notice this a lot if you actually start messing around with like PyTorch or TensorFlow. But the learning rate is like very important. So if you pick a really like crazy high learning rate, like your model won't even converge at all. Like it'll just like get farther and farther away from optimum. So yeah, it's a bit of an art. You basically want to get it so that it's like it's obviously not like the gradients aren't exploding, but you also don't want it to be so slow that your model is like barely training and it takes forever to like converge to a proper answer. Yeah, I would mess around with like some machine learning models if you want to get a better sense of what a good loss is, or sorry, of what a good learning rate is. So with that in mind, yeah, I'm going to pass it to Trevor to talk about linear separability.
All right. So all right. I just want to mention one more thing before I move on to this topic, which is let's see. Yeah, so the task that we were talking about with perceptrons was separating data points, right? Like you separate these red X's and the green circles. Um in this slide, what Christian is doing is he's training a model uh to be like the line of best fit for these points, I think. So yeah, if there's any confusion about that, he wasn't training to like separate the points. It was just to fit the points that he generated. So with that in mind, let's talk about linear separability. So far, all the data sets that we've been working with, so like, let's go back to one of them. So like this one, they can all be separated. They're linearly separable, meaning that they can be separated with a straight line, or like same deal with well, actually not really with this one, but you can pretty much separate them with a line. So a data set that can be separated with just a line, or like if you have a 3D thing, then if you separate it with a flat plane, then it's called linearly separable. So the curveball is, what if we have a data set that looks like this one, where you have a group of red X's here, and you have a group of green circles here and there. Then how do we draw a line to cleanly like separate them, right? Or if we had something like this, where you have like this cool spiral thing, well, we can't really separate the two groups of points with a straight line. And same deal here. So how do we do this with the perceptron? And the answer is that we don't. Um, what we use is a multilayer perceptron. So basically, a multilayer perceptron, or an MLP, is just a bunch of perceptrons that are stacked on top of each other. And the output neurons, so like uh, if you guys look at this, if you pretend to cover up this output layer here and only look at the input and hidden layer, then it's just like one of those perceptrons that output one hot vectors, right? This is just 5 perceptrons in the first layer, each with 4 inputs and 1 output. But the output of each of these perceptrons are fed into a second perceptron that's on top of all of them, into the output layer, into an output neuron. So the output neurons of one layer feeds into the input neurons of the next layer, which gives us the name feed-forward neural nets. And yeah, that's just an example of an MLP. And why do we care about multilayer perceptrons? Well, stacking perceptrons lets the separating line between the two groups of data points, it lets it become non-linear. So imagine like combining linear functions to make a non-linear function. And before we go into this website, I'd just like to talk about one thing, which is I actually lied. MLPs are still linear because they need like a secret ingredient before they can turn into a non-linear function. And before we talk about that, let's talk about why MLPs are still linear functions, right? Because MLPs are a linear combination of linear functions, so they're like a linear combination of perceptrons, and that thing is still linear. That combination is still linear. So what you have to do is you have to introduce a non-linearity into the equation before like slapping a layer's output into the next layer's input. But how do we do that? We use something called an activation function. And activation functions are just nonlinear functions that the output of a perceptron gets passed through. So when you're feeding the activated outputs of one layer into the inputs of the next layer, you no longer perform a linear combination, which means that you get nonlinearity, which is what we're aiming for. So here's just an image of a perceptron, and you got the weights, you got the outputs, you got that sum thing, and then you pass everything through an activation function, and you have this weird symbol called sigma, which people use for people use to represent sigmoid, the sigmoid function, which is this guy. So here are a couple of popular activation functions. The one to the left is the hyperbolic tangent. It's between -1 and 1. Well, the outputs are between -1 and 1. And you got this nice curve going on so that it's not linear. Same thing with sigmoid. The sigmoid is pretty, people like to use it because it outputs between 0 and 1. I think it's not that popular now because this one's actually better, the one to the right, which is called ReLU, which I'm pretty sure it's called. Wait, that's what it stands for. Wait, no, that's like the acronym. I think it stands for rectified linear somethings. But pretty much, if x is greater than 0, then it's just a linear function, and if x is less than 0, then it's a flat line. It just outputs 0. So with this in mind, let's go back to let's take a look at the TensorFlow playground. So I'll switch that. All right. All right, here we go. So basically, this is a pretty cool tool that lets you visualize how a neural net trains. So once everyone's on, let's take a look at this thing. So yeah, I can send. Probably leave the link. Like we'll post a slideshow after the lesson, so you guys can access this anytime. So let's take a look at this. So here's our test set. We've got a bunch of orange points and a bunch of blue points. You can see that this is really non-linear, like not linearly separable. So here's the learning rate, a bunch of parameters that can change. We got some regularization, which Cristian will talk about later. Problem type is classification. Oh yeah. So we talked about two different problem types, right? The thing that Cristian trained is I think it's regression, right? Um, yeah, but anyways, we're concerned about classification here. So we got the learning rate, 0.03 is good. And here's our output. So in this neural network, yeah, so in our neural network, there's 2 input neurons, 4 hidden neurons, and 2 output neurons. And also notice that this is a binary classification task, but there are still 2 output neurons because people just really like one-hot encoding. It's really good, actually. It increases accuracy by a lot. So that's why you usually have 1 neuron for every class when you're doing a classification task. And let's try training this guy. So you pretty much just press the play button. And yeah, with our nonlinear activation function, we get this nice looking separation between the 2 groups of points. But let's try to change our activation function into linear. And if I'm not absolutely wrong, it should not be able to train. You see, because we have a linear activation, we don't have a non-linearity when when we're combining the things between layers, right? So this just stays as a linear function, and it can't separate between the 2 groups because this isn't linearly separable. And no matter how long we try, we won't be able to separate the 2 groups of points because we use a linear activation function, which means that this multilayer perceptron is just a linear function. All right. So let's go back. You guys can tinker around with this after the meet, but let's move on. Um, okay, I'm just gonna share the presentation again. So what? Okay. Activation functions, yada yada. So now I'll pass it back to Cristian, who'll talk about overfitting and underfitting.
Hello. Okay, yeah, let me share my screen. Also, before we move on, I think attendance is up, so if you haven't already, make sure to do that. Let me share. Okay, that should be up. Okay, so yeah, now that we've talked about how to train neural network models and what they are, let's talk about overfitting and underfitting. Yeah, okay. So overfitting. A common issue when training machine learning models is overfitting. It turns out that if you train an ML model too much on a training data set, it can fail to generalize to other data. So it'll actually have a higher loss on your validation data or just other data in general, even though the loss over the training data can still be decreasing as you training. And an easy way to solve this is to only save the weights when the validation loss is lower than the validation loss of all the previous epochs. So here's some pictures kind of visualizing what overfitting looks like. So basically, overfitting occurs when it basically memorizes like the training data too hard. So you can see it here, for example. Even though this like crazy curve technically fits the input data better, you can see how this line is like a much better generalization to these data points, right? Like if I have a data point, let's say here, the overfit model would predict it to be all the way up here, but that's like absurd, right? It must be over here, or like in this area is where you would expect it, not all the way at the top. Let me use this thing, okay? Not all the way at the top here, right? You'd expect it to be somewhere in this area, like here. And then again, we can see it over here. Here's like a properly fit model, has a very clean and very generalizable curve. But this overfitted curve here, it's even though it's technically has a lower loss on the training data, it would probably fail to generalize. It would have a very high error on data outside of the training data set. And then if you visualize, if you actually plot the loss of the training data and the validation data of your model over the epochs or iterations over your data set, it would end up looking something like this. So yeah, your training loss would always go down pretty much, right, as you train. But the validation data loss would actually reach a minimum at some point, and then it would start to increase as your model just starts overfitting to the training data. So yeah, the solution is pretty easy though. Just only save the weights when the current validation loss is lower than all of the other ones, like all the other previous epochs. And then yeah, you can manually see that if your model starts going up in validation loss, it's probably time to cut the training. Cool. Now let's talk about regularization. So another way to prevent overfitting, besides just saving the model when it starts to increase in validation loss, is by actually adding regularization to the model. So different regularization algorithms, for example, L1 or L2 regularization, dropout layers, etc. Dropout layers are probably the most common form of regularization though, and they're one of the simplest as well. They simply turn off a random preset percentage of the neurons each mini batch, and this thins out your model, which can help prevent overfitting. So we can kind of see a GIF of this here. So here you have some dropout layer, and here's the output of some fully connected layer to the output layer, right? But then we add this dropout layer in, and every mini batch, half of the neurons, because we set a dropout to 50%, are just turned off. Like they're just completely not there basically for that epoch. So it basically thins out your model, which can help prevent overfitting. So yeah, same thing here. Instead of being this super crazy dense thingy, you can see how it's much more sparse, and yeah, it turns out that can help prevent overfitting. Okay. Now let's talk about underfitting. So yeah, while your model can overfit, it can also underfit as well. Underfitting is a bit easier to understand. It's just simply when the model is too simple to learn patterns in the data set. It's much less common compared to overfitting, and it's it's a simpler problem to solve, but it can still be an issue. Again, yeah, very easy to fix. You basically just have to make your model more robust, so you can increase the number of hidden layers, in a multi-layer perceptron, or you can increase the width of the layers. And yep, then your model can like encode deeper patterns or more information. So here's like an underfitting model. You can see how probably like a better fit would be something like this, right? But this model just doesn't have the complexity. Maybe it's just like a single perceptron, and it can't encode a function like that. It can't detect a pattern like that. So you just end up getting this line here, which isn't too great of a fit on the data. And I have like a picture kind of comparing them. So again, here's like underfitting. This is regression. You're trying to fit this function here to this data. You can see how when it's underfitting, it just doesn't really encode the data too well. It's not that great of a fit. When you have like just the right parameters, it has a pretty decent fit. You can see how that it's not like overfitting like you can see here, but it's not like encoding like it's still encoding all the information, right? Or at least like a good percentage of it. And then here, yeah, this is just obviously overfitting because it's just being crazy and just like, going through all the points that it can. And then, yeah, here's another regression example. So here's like a degree 1, just like a linear function. And here's like the true function. You can see how this like doesn't encode this at all, even like with the samples. And then with a degree 4, you can see how that's like really good. And then with a degree 15, yeah, that's absurd, right? That's not a good model for this data set. And I guess, Trevor, I'll pass it off to you to end off our presentation.
All right, thanks, dude. So I'll share my screen again. So what's next? We talked about a lot of theory today. What are we going to do with everything that we've talked about today? Next week we'll be doing a sort of coding let's play. So together we'll train a neural network to identify handwritten digits, and we'll be using the MNIST dataset, which is just a dataset of lots and lots of handwritten numbers. So it's a dataset of a bunch of images. We'll learn how to convert these images into vectors, and we'll learn how to make a neural net. We'll learn how to train it, and then we're gonna make something that can classify all of these into ones, all of these into twos, all of those into threes, and so on. So that's for next week. And in the last slide, we've put some extra resources about neural networks and machine learning. The first link is a YouTube playlist about neural networks by 3 Blue 1 Brown. And personally, this is where I first learned about neural nets, and I think it's just pretty good, so I slapped it onto that slide. And if you guys want to dive deeper into deep learning, there are lots of libraries out there that can help you quickly set up and train neural nets in Python. And the most popular ones are PyTorch, TensorFlow, and Keras. So yeah, this slideshow with all these links and the TensorFlow playground and Cristian's REPL example of the perceptron training, all of that will be posted with the slideshow after the meet, which is